Okay guys, so we are going to be moving into mass, mixed problems, some things like that. Last week you watched a few videos from YouTube that talked about how to do a mass calculation, how to do some mixed problems. So now I'm going to go through the notes in this next section, and I'm going to in depth go over what is a mass calculation, what is a volume, what is a particle, and then what happens when you mix those problems together. Okay, so there are three basic, there's more than that, but there are three basic stoichiometric calculations. You have mole to mole conversions, mass to mass, and volume to volume. Those are your three most basic. Okay, all stoichiometric calculations begin with a balanced equation and mole ratios. All right, most of the time you're going to get a worksheet that has the balanced equations, but if you remember last week, you got a worksheet on the mixed problems where they were not balanced. So you did have to go back and balance those. All right. So let's review a little bit of what a mole ratio is. You learned this about a week and a half ago, but it's very important that you understand the concept of a mole ratio, because that's going to be in every single stoichiometric calculation that you are going to do from this point forward. So if you have a reaction in which you have sodium reacting with chlorine to form a table salt, I'm going to go ahead and balance that for you. Okay. So you have 2 sodium plus 1 chlorine yields 2 sodium chloride. Now, when I do these problems, I like to go through and underline what I'm looking for and what I have. Okay? So how can you determine the number of moles of table salt? So I'm looking for moles of table salt and produced from 0.02 moles of chlorine. So chlorine is what I'm given in the problem. That's already what I know. So when you start this problem out, you're going to start it out with 0.02 moles of Cl2, because that's what I have. I'm looking for sodium chloride. Okay? So when you do the mole ratio, it's always called don't overdo. What I don't know over what I do know. So in this problem, you're going to have 2 moles. So this is where you use the balanced equation. Whatever the coefficient is in front of the molecule or compound or whatever you have in your reaction, that's the number of moles you have. So in our case here, it's I don't know sodium chloride, so I have 2 moles of NaCl over 1 mole of Cl2. So don't overdo. It's what I don't know over what I do know. I do know chlorine because that's what they gave me in the problem. So that's why I started my problem off with 0.02 moles of chlorine. And then I'm converting from moles of chlorine into moles of sodium chloride. Okay? So it's don't overdo. So now I'm going to take this number and times it by a ratio of 2 over 1. So that's going to give me 0.04 moles of NaCl. So this right here is my mole ratio. This is what I'm going to be using in every single problem. Mass, volume, particle, my mixed problems. So what I'm using it for everything is this mole ratio. You have to use that to go from one thing to another. Okay? So that's just a little review. Now, moving forward to mass calculations. So first of all, you write a balanced equation for the reaction. Okay? You need to make sure your equation's balanced. That's the first step. The second step is you write the given mass on a factor label form. Factor label form just means those ratios that you see me set up, like when we did dimension analysis, where you're multiplying fractions. That's what they mean with a factor label form. Okay? Third step, you're going to convert mass of reactant to moles of reactant. So this is where you're going to take the grams given in the problem, and you're going to convert that to moles by using the molar mass of the given compound. Remember, molar mass was where we take the atomic masses from the periodic table and you add up how many you have of them. Okay? Then the fourth step is convert moles of reactant to moles of product. That's what I just showed you an example of. It's don't overdo. What I don't know over what I do know. Okay? So you're converting the unknown with the known by using the balanced equation. And then the final step is you're now going from moles of what you're looking for, moles of your X, to grams of your X. And you do that by using the molar mass of your unknown. So it's a set pattern that you're going to follow for all of the mass calculations. You're doing the same thing, it's just you're using different compounds, so you're going to have different masses. So let's do an example problem. So in this problem, I have a furnace burns an amount of coal containing 100 grams of iron 4 sulfide. So I'm going to go ahead and underline 100 grams because this is what I know. So I'm going to go ahead and underneath, I'm going to write 100 grams. This is what I'm given, okay? Then it says how much SO2 is produced. This is what I'm looking for. So I'm going to go ahead and underneath there, I'm going to go ahead and put my X because that's what I'm trying to find. Now, when you set up a problem, start out with number 1. Make sure your equation's balanced. My equation is balanced. Step 2, I'm going to convert grams of my known into moles of my known. So you're going to start out and you're going to write 100 grams of FeS2 over 1. Every time you start a mass problem, you always start with whatever you were given in the problem, the number of grams given. The next step is you're always going to have 1 mole on the top because we're using the molar mass. And the grams down here are going to be for the substance that we started with. So what you're going to do is you're going to add up the molar mass of FeS2. So Fe has an atomic mass of 55.85, and you're going to add that to 2 sulfurs because you have S2 here. So you're going to say 2 times 32.06, which is the atomic mass of sulfur, and you're going to get 119.97 grams. Okay? And that's what goes down here because you're taking grams of this, canceling grams out, and converting into moles of FeS2. Now your next block, this is where the third block is always going to be the mole ratio, what we just talked about a minute ago, where you're going, what I don't have, so don't overdo. What I don't have over what I do have. Okay, so this is where you're going to use your balanced equation. I don't know sulfur dioxide. I do know iron sulfide. So when I do my mole ratio, it's don't overdo. So we're going to have 8 moles of SO2, okay, over 4 moles of FeS2. And then the last block is where we're going to take number 4, where we're going to convert moles of our SO2 into grams of our SO2. So we put 1 mole on the bottom, and we put grams of SO2 here. Now what are the grams? We have to add those up. So we have to add S plus 2 oxygens. So 32.06 plus 2 times 16 is going to give me 64.06. Okay? Now, the last step is we're going to calculate. You multiply everything on the top, and then you multiply everything on the bottom, and then you divide the 2 numbers. So I'm going to put in parentheses, I'm going to say 100 times 8 times 64.06, end the parenthesis, and then divide by, and then put this in parentheses, 119.97 times 4, and I get 106.8. So my answer here, and I'm going to have to write that kind of underneath, is 106.8 grams of SO2. Okay? So I wrote it down here, 106.8. Now, go ahead and try that in your calculator. Make sure you get the right number when you multiply and divide. Okay? So that is how you do a mass calculation. Okay? Now, what if instead of mass, we're trying to do volume? Okay? So in terms of moles, Avogadro's principle states that equal volumes of gases at the same temperature and pressure contain equal numbers of moles of gases. Now, this should be a review for you because this is over chapter 10 when we did converting from volume to volume there. The only difference here is we were using the same compound when we were converting from liters to moles or moles to liters. Now we're going to use a balanced equation, and we're going to be converting a volume of one substance, a gas of one substance, to the volume of a gas of another substance. Okay? So the molar volume of a gas is the volume that a mole of a gas occupies at a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. So under these conditions of STP, the volume of 1 mole of any gas is 22.4 liters. like the molar mass, the molar volume is used in stoichiometric calculations. Okay? So let's do an example. So I have nitrogen monoxide and oxygen gas combined to form the brown gas nitrogen dioxide, which contributes to photochemical smog. How many liters of nitrogen? So that's the first thing I'm gonna underline. And that's gonna be my, nitrogen dioxide. So that's my X, are produced when you have 34 liters of oxygen gas. Now, it's going to tell you it reacts with an excess of nitrogen monoxide. That's important for the reaction, but it's not important for what we're doing. They're always going to give you a little bit of information, and that's why it's important to underline whatever follows the word how many, and then underline whatever follows the number. So I would also underline 34 liters of oxygen. Okay? So this means that in this problem, even though nitrogen monoxide is important for the reaction, it's not important for the information we're trying to find. These are the only two things that are going to be involved in this reaction. So we'll start out with 34 liters of oxygen over 1. Since we're using molar volume, not mass, we don't have to add up the molar mass of oxygen. You're going to use 22.4, which is my molar volume, to convert from liters to moles. Then the middle one is just going to be your molar ratio. Don't overdo. What I don't know over what I do know. Okay? So you're going to have 2 moles of NO2 over 1 mole of oxygen. It's 1 mole of oxygen because remember, 1 is understood. So it's going to be a 1. And now since we're going to volume, we don't have to do the volume, we do the molar mass. We're just going to use 22.4 again. So we're just going to take 22.4 liters over 1 mole. And some of you may see, if you're looking at this, that guess what? The volumes cancel out. And yes, they do. Okay? Because you're converting into volume both times. Now, if I threw something in like mass or particles that we were solving for, this number would be different over here. Okay? But when you're doing a volume to volume problem, you'll have 22.4 here and 22.4 here, which they do cancel out. So in essence, it becomes like a mole to mole ratio problem. So you're going to take 34 times 2, which is going to give you 68 liters of NO2. Okay? So your answer should have been 68 liters. All right? All right, so let's try one more. What volume of oxygen must be used to produce 2.5 liters of CO2 at STP? So we're looking for oxygen, that's our X, and we have 2.5 liters of CO2. So we start our problem with 2.5 liters of CO2 over 1. Okay, we have 1 mole here, 22.4, because we're dealing with molar volume. You have your mole ratio, don't overdo what I don't know over what I do know. So 6 moles of O2 for 6 moles of CO2. And then the last block is going to be 22.4 liters over 1 mole. And it's going to end up equaling 2.5 liters of oxygen gas. Okay? So we've got one more thing to go over, and that's particles to particles, and then you guys are going to have an assignment over this. Okay? Now, particles to particles is going to be just as easy as volume to volume, because once again, you don't have to calculate the molar mass. Instead of using molar volume here, now you're going to use Avogadro's number, which is 6.02 to the 23rd power. So you're going to convert from atoms, ions, or molecules, okay, to moles, and then back to particles, just like we did with volume. So in this problem, it says how many molecules of KClO3, okay, so that's what we're looking for, are decomposed if you produce 8.24 times 10 to the 25th molecules of oxygen. So this is going to be our given, which is 8.24 times 10 to the 25th. So we're going to start this out over 1. And just like we did before, 1 mole is still going to be over here, just like the mass to mass, just like the volume to volume. But now the number that goes here instead of 22.4, instead of molar mass, is going to be Avogadro's constant, which is 6.02 to the 23rd power. And the middle block will still be mole to mole ratio. It's what I don't know over what I do know. So you're going to have 2 moles of KClO3 over 3 moles of oxygen gas. And then finally, the last block is going to look just like the one in number 2, the second block, except now we're going back to particles. So the particles are going to go on the top over 1 mole. So in essence, just like molar volume, this and this will cancel out. So you'll end up with just the mole ratio. So you'll say 8.24 times 10 to the 25th, and you're going to multiply that by 2 and then divide it by 3. Which is going to give you, I might have to write, I don't have room to write it, so I'm going to kind of write it up here next to the sample problem. So that's going to equal 5.49 times 10 to the 25th. Okay? And you would then write molecules of KClO3 for your unit. Okay? All right, so following this video, you guys are going to have a worksheet on volume to volume, particles to particles. I also did a little bit of a review on the mass in case you were struggling with that and you need to go back and fix any of those problems, okay? So I'll talk to you later when we're going to be talking about limiting reactant and excess reactant, okay?